Welcome. This lesson is on thermal boundary layers, and thermal boundary layers occur when there's a heated surface and then there's flow past that surface. And in particular, we're going to look at an example of laminar flow over a flat plate that's heated, and there's a velocity V infinity far away from the plate, and also a temperature T infinity far away from the plate. And then the plate is heated at temperature Ts. And we form both a momentum boundary layer and a thermal boundary layer. In the momentum boundary layer, the velocity goes from 0 due to no slip on the surface of the plate up to V infinity outside the boundary layer. And there's both viscous effects and inertia important in the boundary layer. And then in the thermal boundary layer, the temperature goes from T at Ts at the surface down to T infinity outside the boundary layer. And both conduction and convection are important in the thermal boundary layer, which has thickness del T. Now, an important parameter is the Reynolds number, and the Reynolds number has to be large for there to be a boundary layer. And it's, as you probably know, it's proportional to V infinity times the characteristic length, which is the length of the plate, and divided by the kinematic viscosity, which is the shear viscosity divided by the density. Another important parameter is the Prandtl number, which is the kinematic viscosity divided by the thermal diffusivity. Thermal diffusivity is the thermal conductivity of the fluid divided by the density of the fluid and the specific heat. And the Prandtl number is a little bit over 1 for simple liquids like water and a little bit under 1 for gases. It's much larger than 1 if you have a very viscous fluid like an oil or a polymer melt. It's very rarely much less than 1. The only exception would be a liquid metal like liquid mercury. Now, another parameter of importance is the Nusselt number. And the Nusselt number is a dimensionless heat transfer coefficient made dimensionless with the thermal conductivity in the denominator and the length scale of the plate in the numerator. And that's our goal, is to find the Nusselt number, because then we can find the area average heat transfer coefficient H with a bar over it. So we'll start by looking at the heat flux from the surface, Q double prime, which has units of, say, watts per meter squared. According to Fourier's law, it's the thermal conductivity of the fluid, and the fluid in particular, because the heat transfer is through the fluid, times the temperature gradient. And the temperature gradient, the component we're looking at is in the y direction, because that's normal to the plate. And we're evaluating it on the plate, which is at y equals 0. Okay, and this can also be set equal to a heat transfer coefficient times the temperature difference between the plate and the ambient fluid. And that heat transfer coefficient would be to be found, and that's called Newton's law of cooling. We'll start with a scaling estimate. And so we're going to estimate that temperature difference or temperature derivative as the temperature difference at the top of the boundary layer minus the temperature on the plate divided by the thickness of the boundary layer. And that's an order of magnitude estimate for that derivative. And then we can plug that into Fourier's law, and we get an estimate for the heat flux. And it's inversely proportional to the thickness of the boundary layer. That also allows us to get an expression for the heat transfer coefficient, H, which would be proportional to the thermal boundary layer, the thermal conductivity divided by the boundary layer thickness, and you get that by plugging this result into here. And what you see is that since the boundary layer varies with distance and generally increases, the heat transfer coefficient will decrease with distance from the edge of the plate, and therefore the heat transfer coefficient is a local heat transfer coefficient. And the Nusselt number, which is based on the area average heat transfer coefficient, we can see scales as the length divided by the thickness of the boundary layer. And this is often much greater than 1 because the boundary layer is quite thin. And that would mean that the convection is very important and we have high heat transfer rates. Now, in order to evaluate the Nusselt number, we need to know the thermal boundary layer thickness. And to do so, we look at the thermal energy equation, and we'll assume constant properties in steady state and no generation of heat in the fluid. And therefore, we just have convection equals conduction. We'll do a scaling of the convection terms, and we'll look at the first term of a scaling for the velocity in the x direction is V infinity. The temperature difference goes from Ts on the right-hand side after the fluid has been heated up to T infinity on the left-hand side where it comes in, and that takes place over a distance L in the x direction. The convection in the y direction is actually of similar magnitude. Del y is smaller, but Vy is also smaller. And then finally, for conduction, the order of magnitude for conduction would be the thermal diffusivity times the temperature difference again, and then divided by the length scale squared. And here the length scale is much smaller for conduction across the boundary layer than along the boundary layer. So the second term dominates, and that length scale is del T. And it's squared because we have a second derivative. Now we can equate conduction and convection in the thermal boundary layer, and that gives rise to this expression here, which tells us the boundary layer thickness grows with length to the 1/2 power, so it grows along the plate. It also grows with increasing thermal diffusivity alpha. Stronger heat conduction means the boundary layer will be thicker, and it's inversely proportional to the square root of the velocity. Stronger velocity means stronger convection that would convect the heat away. And this scaling holds for Prandtl numbers of order unity, so simple liquids and gases. There's a slightly different scaling if the Prandtl number is large, because then the boundary layer is thinner. The thermal boundary layer is thin compared to the momentum boundary layer, and the velocity in that thermal boundary layer is lower, and there's a different scaling. I'll say a little bit more about that in a minute. And then finally, our dimensionless heat transfer rate, which is the Nusselt number, scales as the length of the plate divided by the thermal boundary layer thickness. We can use this result in that equation, and that gives us the following expression. This quantity here, it looks a little bit like a Reynolds number, but it actually is called the Peclet number. And of course, it's raised to the 1/2 power. And it shows that the heat transfer increases with velocity, increases with the length of the plate, and then decreases with thermal diffusivity. That's actually the Nusselt number. The actual heat transfer rate will increase with thermal conductivity, as you would see when you calculate the heat transfer coefficient. Now, the Peclet number is equal to the Reynolds number times the Prandtl number. And so this scaling gives us Reynolds number times Prandtl number to the 1/2. And this is an approximation or an order of magnitude estimate. If we do an exact analysis using a similarity solution, you'd get a solution of about 0.65 times Reynolds to the 1/2, Prandtl to the 1/2. An empirical correlation is given here, which also is 0.65 Reynolds to the 1/2. But in this case, Prandtl number is multiplied to the 1/3 power. And that's because the experiments were done for Prandtl numbers near 1 and much greater than 1, and where we would have that different scaling. And the 1/3 power gives the different scaling. And then finally, once you have the Nusselt number, you can calculate the area average heat transfer coefficient from the equation above. It's just the Nusselt number times the thermal conductivity divided by the length, and then we're done.